Lecture 1, Module 2, Introduction to Six Sigma. What is Six Sigma? Six Sigma is a statistically based project management methodology developed at Motorola in 1986 and focuses on reducing variation and improving processes. Six Sigma combines statistical tools with project management tools. The statistical aspects are nothing new, as you saw in the introduction. Six Sigma is simply built off of decades of earlier quality improvement methodologies such as the total quality management and zero defects movements. Six Sigma is based on a systematic project management structure called DMAIC. What is DMAIC? The basic DMAIC methodology consists of the following 5 steps. D. Define the problem with the system, what the business or customer needs are, and create a project around them. Measure the current system and collect appropriate data on it, and we'll discuss appropriate data in the measurement section. Analyze the data to verify cause and effect relationships, determine what the relationships are, and attempt to ensure that all factors have been considered. Don't overlook anything. Improve or optimize the system based upon data analysis using techniques such as design of experiments, which we will go over in the future lectures. And finally, control, to ensure that any deviations from target are corrected before they result in defects. Set up pilot runs to establish process capability, move on to production, set up control mechanisms, and continuously monitor the process. Sounds like PAT, doesn't it? The Six Sigma project management structure really is an implementation of the scientific method. The scientific method consists of the following steps, pretty much. First, you define a question. What is it that you wish to know about a natural system? Observe and measure. Observe a natural system and collect data on it. And analyze. Analyze the collected data and form an explanatory hypothesis about that natural system. How does it work? And improve. Maybe perform experiments and collect data, testing the hypothesis, analyze the data, interpret the data, and draw conclusions about the natural system. Well, of course, we don't try to improve nature, we just try to measure it. And control. Continue to test the natural system, improving the test procedures, improving accuracy and precision, and standardizing technique to gain better insight into that system. So in a nutshell, the DMAIC process of Six Sigma can be explained easiest as shown in the table below. First, we take a practical problem, and make it into a statistical problem by measuring it. Then we develop a statistical solution through the analysis, and transform it into a practical solution through the improve and control steps. Six Sigma is derived from the field of statistics known as process capability studies. Six Sigma was initially focused on improving manufacturing processes, but it also now includes business systems, in order to minimize the number of units produced out of specification. A Six Sigma process will have a defect level below 3.4 defects per million opportunities, also known as DPMO. The goal of Six Sigma is to improve all processes to this level of quality. Six Sigma looks at the variability of a process, and here we see a process with a target centered in the middle on the target line, and the variability shown by the tails to the left and to the right. And we compare it to its specifications. So here we see the specification range and the process within it. Process capability is defined as how well a process fits within its specifications. Process capability is the ratio of the specification range to the spread of the process. The process spread is measured as 6 times the standard deviation of the process. So here we see a specification range of 6, and we have 1 standard deviation. So specification range times 6 standard deviations. So 6 times 6 divided by 6 times 1, 6 over 6 equals 1. So that's a perfect fit, theoretically. In this case, the process fits perfectly within the specifications, almost, and we'll discuss this a little bit later in the course. Simply put, Six Sigma is an organized set of practices designed to improve manufacturing processes and eliminate defects. In Six Sigma, a defect is defined as anything that could lead to a customer, and sometimes in our case, many times in our case, the patient dissatisfaction. So should Six Sigma be focused on those aspects of our manufacturing processes or businesses that we really don't understand? Heisdeck's law. Most of what you know is wrong. A variation on Mark Twain's, really, It ain't what you don't know that gets you into trouble. It's what you know for sure that just ain't so. There are many myths in life, and the world of pharmaceutical manufacturing is really no exception. There are many practices that cannot be traced to an actual or valid source. For a long time at some pharmaceutical companies, incoming lots of raw materials were sampled using the formula square root of n plus 1. If you asked, no one knew where the formula came from or could really justify its use. It was finally dismissed after a statistician, Hewa Saranadasa, who I worked with, this published an article in Pharmaceutical Technology really refuting its validity. It's okay, but it gives you incorrect results in many, many cases. However, it's still in use. As a matter of fact, the book has just been published saying that you can use it by a statistician. Go figure. Moral of the story, in Six Sigma, when looking at a manufacturing process or business system, never assume anything is valid. Challenge everything. Well, why Six Sigma? Why would you even bother doing it? Let's look at how Motorola came to develop Six Sigma in the first place. Essentially, a Japanese company had taken over a Motorola plant and had quickly started making higher quality products, 1/20th the number of defects of the other Motorola plants. They did this using the same workers, same equipment, same technology, everything, and lowered costs. Clearly, the only difference between the Japanese and Motorola was the management, how it ran the company. The Motorola executive management finally had to admit, our quality stinks. Motorola's CEO started a process for improving quality in the company that became known as Six Sigma and eventually resulted in a Malcolm Baldrige National Quality Award in 1988. Now let's look at how Six Sigma affects quality. As the process capability improves and the Six Sigma level increases, the rate of defects drops exponentially. As you can see, at 3 Sigma, you have 66,000 defects per million. Many, many defects. Lots of waste, lots of money going out the window. Well, how much money? Decreasing defects is very good, but improving quality is not the only benefit that Six Sigma brings to a company. General Electric found that the costs associated with poor quality are very high. Non-Six Sigma companies typically spend 25 to 40% of their revenues fixing quality problems. It costs money to cull out the bad product, destroy it, document it, all that kind of stuff. So the cost of poor quality versus Six Sigma level, if we're only at 2 Sigma, it's almost 50% of the cost is going towards disposing of these things. Not good. Successful Six Sigma programs can have a dramatic effect on the company's bottom line, hence the interest in them. As stated earlier, Six Sigma is simply an application of the scientific method to manufacturing processes and business systems. The name Six Sigma implies moving a manufacturing process or business system to a point where the process capability is equal to 2, which is Six Sigma. In terms of quality, this means the number of defects for that process would be only 3.4 in a million opportunities. Remember the 66,000? Down to 3. Lots of savings. Let's look at moving a 3 Sigma process to a 6 Sigma process. So here we see a specification range of 12. And we have a standard deviation equal to 2. So specification range divided by 6 standard deviations would be 12 divided by 6 times 2. So that gives us a 12 divided by 12, or a 1. So what we're going to do with that process is tighten up the variability. We will make it less variable. So now we've reduced the standard deviation to 1, cut it in half. And now the specification range divided by 6 standard deviations is 12 divided by 6 times 1, which is 12 divided by 6 equals 2. The defect rate for a process capability of 2 is usually expressed as 3.4 defects per million opportunities. Actually, the true value is 0.002 defects per million opportunities. Well, that's a very, very big difference. Why is that? Well, in Six Sigma, it is anticipated that even a good process can shift about the target 1.5 Sigma in either direction. So the DPMO for a Six Sigma process is just calculated at the 4.5 Sigma level, giving the 3.4 DPMO value. So as you see there, you could go 1.5 Sigma to the right or to the left, so it's recalculated as 4.5. Now there's lots of criticism of this. Some statisticians have criticized the 1.5 Six Sigma shift is not really appropriate. The 1.5 Sigma shift results in stated 6 Sigma levels that actually corresponds to 4.5. So by Six Sigma definition, a 4.5 sigma process will be designated as a Six Sigma process, even if there is no measured shift in the process, which is true. Therefore, the current Six Sigma scoring system does not really correspond to the actual measured standard deviations. And this has been a major complaint about how Six Sigma has been implemented. It's not necessarily wrong, it's just overstating the defects. A major part of Six Sigma is measuring quality in terms of the number of defects. Where quality in the past used to be measured for defects in percent, parts per 100, and I experienced that, quality in Six Sigma is measured for defects in parts per million. As Six Sigma levels increase, the number of defects decrease dramatically. So here we see the Six Sigma level running from 3 up to 5, and you can see the dramatic drop in the number of errors and per million opportunities, or defects per million opportunities. While Six Sigma addresses quality, its success lies in that it also addresses the business. It is a business philosophy that increases profits by improving quality and productivity. There are 3 important aspects to Six Sigma: project management, statistical and process improvement tools, and culture change management. Notice that it is bolded and italicized. Very, very important. Six Sigma can improve processes, it can reduce defects, and it can yield major reductions in cost, but to do this, it must be successfully incorporated into a company's culture. Humans, and therefore workers, tend to be creatures of habit. Once a habit is formed, it becomes hard to change it. This tendency transfers to and infects business practices. Once business systems are in place, they become very hard to change. But ability to change business practices, including rapid change, is becoming essential for long-term survival in today's global business environment. Let's look at the U.S. automobile industry. They've been struggling for decades with business pressures coming from global competition, poor quality, high labor costs, credit difficulties, high gasoline prices, etc., etc. The U.S. automobile industry clearly needed to change many of their business practices to survive. But how ready to change is an industry that had a worldview very similar to Henry Ford's. Henry Ford is famous for having said, "The customer can have any color he wants as long as it's black." At that time, that was the only paint that he could work with easily, so that's the color you got. These days, the customer can ask for just about any color he wants on a car and can specify and customize the car to his taste. That is what will satisfy the customer and is the way the business has to go. If you have the attitude of you can have any color you want as long as it's black, you will be out of business, and that almost happened to the industry. Now, up until the early 90s, the U.S. pharmaceutical industry had been a highly profitable business. Unfortunately, this was mainly due to the unrestricted ability to simply raise drug prices every year, which didn't get noticed because it was being paid by the HMOs. There was never a need or a desire to run the business efficiently. This all changed under the threat of healthcare reform during the Clinton administration. The industry was possibly facing price controls, and double-digit growth by raising prices was no longer viable. The industry now needed to consider cost-saving measures, but really had no experience in such things. I recall even the industry described itself, I heard a director at a presentation say, "We were dumb, fat, and happy." And that's still somewhat true. The U.S. pharmaceutical industry needed something comprehensive to make gains in the area of cost savings and turned to programs such as Six Sigma and lean manufacturing, which we'll discuss later, to achieve the savings they required. The impressive savings experienced by General Electric made Six Sigma look like just the kind of program the industry needed. When we look at this table here, the purple line are the costs of implementing Six Sigma, and the blue line are the benefits of implementing Six Sigma. As you see in 1996, GE, the costs exceeded the benefits, but quickly the benefits far exceeded the costs. So there was a very, very strong payback on the investment. So we're saving millions and millions of dollars for less than $1 million worth of expense. But moving to Six Sigma requires a major change in the culture of most pharmaceutical companies. Wasteful practices have been ingrained in the culture of many pharmaceutical companies. Workers, in particular managers, were now expected to look for waste in their operations. This is perceived as dangerous. If you volunteer that there are wasteful inefficiencies in your department, what does this say about your management abilities? That as a manager you run an inefficient and wasteful department? Such admissions could lead to cuts in your budget, cuts in your employees, even merging of your function into another department, and maybe even elimination of your job. Who's going to volunteer for that? So Six Sigma programs in the pharmaceutical industry have been typically met with resistance by pharmaceutical workers. Many workers find just the idea of Six Sigma programs very threatening. Industry layoffs have only increased the distrust of the intent of Six Sigma programs. Why are they bringing this program in here? To cut more jobs. So there's not going to be a lot of support. Industry layoffs have also decreased the number of workers available for performing Six Sigma projects. These are usually done on top of your job, not in replacement of your job. In some cases, those workers performing Six Sigma projects do so slowly and really with little intent to improve things, especially if they don't see their bosses supporting it. Culture change is probably the biggest hurdle to success, and when working on a Six Sigma project in the pharmaceutical industry, you must be keenly aware of this issue. Examples of project problems due to cultural resistance will be discussed during this course. Before you can make any significant business change, though, you need to understand what to change. The following are the typical key business drivers for any company: profit and costs, market share, customer satisfaction, efficiency of the operation, product differentiation. Six Sigma has moved beyond just manufacturing to areas like service and even into R&D. Just about anywhere in the organization, parts of it can be employed. In pharmaceutical manufacturing, the most important business drivers generally are profits and costs and efficiencies. So this course will focus on these drivers. Business metrics. Before you can improve any business drivers, you need to be able to measure the improvement. To do this, you need to establish some kind of metric system. Metrics are something you measure about your business. These metrics will be different from company to company, but for pharmaceutical manufacturing, they are usually financial metrics, process metrics, and quality metrics. Pharmaceutical manufacturing metrics. Some typical metrics for pharmaceutical manufacturing might be something like this. For financial metrics, are labor costs, the total hours for a department. Process metrics, the cycle time, how many hours spent compressing a batch of tablets, let's say. Quality metrics, the defects produced, the number of rejects per packaging lot. Now, how do you pick your projects? Project selection is vital to the Six Sigma program's ultimate success. You pick the wrong projects and don't save any money, you're not going to be successful. Every company has their own approach for Six Sigma project selection. Since pharmaceutical manufacturing tends to be project rich, some companies just go after the low-hanging fruit, which is not necessarily a bad approach. And some companies will only go after Six Sigma projects that have cost savings of $500,000 or more. That's generally to make sure they offset the cost of implementing the program. Here are some typical criteria for selecting a project. You would want to look at its scope. Now, is this project just a local project? Is it division-wide, or is it global? It can be a small scope or a very large scope. What's the impact? How much money, how much time, or combined can be saved? If a lot of money can be saved, you may want to do that. Urgency, how soon is it needed? It may be even something that has compliance related to it. Risk, what is the risk of not doing it? There could be huge costs or even, like I said, compliance issues with not doing it. Difficulty, will it be an easy kill or will it be something very hard to accomplish, highly technical and all kinds of people involved? Now, Six Sigma program structure. One important reason for the general success of Six Sigma is the martial arts structure of most Six Sigma programs. Most of these programs have a structure of master black belts, with black belts under them, and green belts. Yellow belts, maybe, these are newer, and white belts, maybe, these are also newer. Many workers find this martial arts structure very attractive, and there is a strong desire to achieve black belt or even green belt by many workers. What are master black belts? They should be highly proficient in Six Sigma methodologies. They should have advanced expertise in areas beyond black belts. They should have good knowledge of statistics, good project management skills, understanding of IT, etc., etc. They train and mentor the black belts. They also certify black belts and even green belts. Black belts usually have 2 weeks of advanced training, and they should master the black belt body of knowledge that's associated with their program or whatever they're being certified under. As we said early in this course, the body of knowledge varies considerably from program to program, university to university. The black belt independently will run his or her Six Sigma projects. They will also oversee green belt Six Sigma projects and help them with their projects. and they train and mentor the green belts and recommend green belts for certification when they think they've accomplished enough. Now note, some company programs offer 2 levels of black belts. Some of them are project management based black belts, and then others are more statistics based. So depending on what your preference is, if you have a strong project management background, you may gravitate towards just the project management black belt and may not be as strong in statistics. Green belts typically get 1 week of training, and they're supposed to master the green belt body of knowledge. Again, there's variability in that. And they work on Six Sigma projects under the supervision of a black belt. They need to complete at least 1 Six Sigma project to get certified. Yellow belts and white belts. These are the newer introductions into the Six Sigma arena and even come with some certifications. One Six Sigma website jokingly asked whether a white belt was certification or certifiction. So there's a little bit of disdain about these lower level belts. Training is 2 days for yellow, 1 day for white, and the relative value of training is not well understood, but like as I said, considered by many to be not that important, insignificant, or even maybe irrelevant in some people's eyes. However, some companies use white belt training to spread understanding about Six Sigma throughout the company. This is not a bad idea. This may help solve the problem of the perceived us versus them that can stymie many programs. If some of the company workers are seen as being selected and elite, getting the green belts and black belts, while the rest of us are struggling to do our jobs, there will not be support for the program, and the program may go under. So it may be a very good idea to start the program with white belt training for everybody and then progress upward.